Hello everyone. In this lecture, we will look at how we can visualize the distribution of a dataset. So when we are dealing with a dataset, one of the first things that we want to do is to get a sense of the distribution of the variables. So in this lecture, I want to cover how we can examine univariate and bivariate distribution. Let's start. So we will look at, let's first import the library. So we have import numpy as np. We will import pandas as pd. We will import cborn as sns. Import matplotlib.pyplot as plt. And then finally, from scipy, we want to import stats. So this is something new, what we hadn't done earlier. The first thing I want to show you is how we can plot univariate distributions. Now, the most convenient way of doing this is to use the dist plot. And remember, by default, this will draw a histogram and it will fit it into a KDE, which is the kernel density estimate. So the default is a histogram and fit is the KDE. So X is np.random.normal. Let's keep the size as 100. sns.displot X, and the result is like this. So we can see a distribution. If you keep on running it, you notice the result obviously keeps on changing because we're using random numbers here. Now, histograms are familiar, and a hist function also exists in matplotlib. A histogram represents the distribution of the data, and it forms bins or categories along the range of the data and then draws bars to show the number of observations that fall into each bin. Let's illustrate this. So for this example, I want to remove the density curve and add what we call a rug plot. So we're adding a rug plot. Simple, displot X. We will purposely keep our KDE as false because we want to turn it off. And we will turn on our rug like this. And it's called a rug plot because it looks like a rug. So when you're working with histograms, the main choice that you have is the number of bins to use and where to place them. Now, displot uses a very simple rule to make a good guess for what is the right number by default. But if you want to try more or fewer bins, you can do that as well. So here I want to show you how you can control the bins as well. So we will also have to say that bins is equal to 20, right? And you can notice you can keep on tweaking this to see what would be the right number of bins, which would make your data appear the most impactful to the end user. So I had already mentioned the KDE earlier. So let's look at the KDE once again. Now KDE, like I said earlier, is a very useful tool for plotting the shape of a distribution. Like the histogram, the KDE plots encode the density of observations on one axis and the height along the other axis. So if I say displot X, we will keep our hist as false. So basically we're turning off the histogram, and we will keep our rug as true. We will only see this, right? Now, do remember that drawing a KDE is computationally more involved than drawing a histogram. So what happens is that each of the observations is first replaced with a normal Gaussian curve. So I'll just write it down here. So computationally more involved, and each observation is replaced with a normal, or what we call a Gaussian curve, and this is centered at that value. For most of you, this would not really be required, but I just want to illustrate this. Even if you understand 10-20%, that's okay. This is not something you will need to use in actual business use cases, but it's good to know theoretically how this works, right? So you can just follow the steps and just try to copy and paste it and see how this works. So the bandwidth is 1.06 into STT into x dot size, and then we want to say minus 1 divided by 5. Then we have our support, which is np dot line space minus 4, 4 and 200. Okay, then our kernels right now are nothing. Then we'll run a simple loop. Kernel stats norm x underscore I. Then we select our bandwidth, and then dot pdf support kernels dot append kernel plt dot plot support kernel. Let's keep the color as green. So we're almost there. The final thing we want to do is to create our SNS dot rut plot x. The color is equal to, let's say, 0.2, and the line width is equal to 4, right? So like I said earlier, you don't really need to understand how this works. In case your work requires you to work with Gaussian curves, then you can look at this. Otherwise, you can skip this. So what happens is that once these are created individually, then these curves are summed up to compute the value of the density at each point in the support grid. And the resulting curve is then normalized so that the area under it is equal to 1. So just to complete the illustration from SciPy, and this is the reason I imported SciPy in the beginning. I'll import traps. The density is equal to np.sum. Kernels axis is equal to 0. My density traps density comma support, and then we have PLT plot and support density, and the result will look like this, right? So we can see that if we use the KDE plot, we get the same curve. For example, if I just write my SNS.kde plot x, and let's also shade it, exact same result. So this function is used by the displot, but it provides a more direct interface with easier access to other options when you want just the density estimate. For this, you can use the KDE plot. All right. Now the bandwidth, which is the BW parameter of the KDE, controls how tightly the estimation is fit to the data. So think of this like being similar to the bin size. So we're looking at the BW, which is equal to the bandwidth. And while it's not the same, you can consider this to be similar to the bin size of a histogram. So it corresponds to the width of the kernels that we plotted above. All right, let's take an example. So sns.kde plot. Then we have sns.kde plot x, the bandwidth is equal to 0.2. The label, you can write anything you want. So I'm just writing bandwidth and 0.2. Again, sns.kde plot x. Then we have our bandwidth, and this time we'll keep it at 2. And the label is BW and 2. So PLT legend. And the result looks like this. So as you can see, the nature of the Gaussian KDE process means that the estimation extends past the largest and the smallest values in the dataset. So is it possible for us to control it? Absolutely. So we can control how far past the extreme values the curve is drawn with the cut parameter. So we look at the cut parameter now. But remember, this will only influence how the curve is drawn and not the fit. So only influences the curve, not the fit. Just remember this. So sns.kde plot x shade is equal to true, cut is equal to 0. Then we have sns.rug plot and x, right? So we get a result like this. Let's also see how we can fit parametric distributions. So we can use the disk plot to fit a parametric distribution to a dataset and visually evaluate how closely it corresponds to the observed data. So x is equal to np dot random and dot gamma 6, and size is equal to 200. And then we have our disk plot x kde is equal to false, and the fit is equal to stats dot gamma, right? So we can see the histogram and the curve together. Let us plot bivariate distributions now. For this, we have the joint plot. So let's take an example. Now, scatter plot, we know, is one of the most common familiar ways to visualize a bivariate distribution, where we have the x and the y values. So this is analogous to a rug plot on 2 dimension. So we say sns dot joint plot, and we say that x is equal to x, and we say that y is equal to y, and the data is equal to our data frame. So I just quickly create the data frame as well. So mean and my covariance, let's keep it at 0 and 1. Then we have 1 and 0.5, and finally we have 0.5 and 1. So let me just quickly check that. So we don't need to close this here. And then data is equal to np dot random dot multivariate underscore normal, and we'll use mean and covariance with, let's say, 200. And then our data frame would be pd dot data frame data, and our columns are, I'm just going to call them x and y. So x and y, like this. Let's run this and we can see the joint grid like this. Okay, now I want to show you something really cool. This is called the hex bin plot. So you can consider this as an equivalent to the, so like a bivariate equivalent to the histogram. It shows you the count of observations that fall within the hexagonal bins. Now, typically it works best with a large data set, but you can try this with a smaller or moderate size data set as well. Right, so we say x, y, np.random, then we have dot multivariate underscore normal mean and covariance 1000 dot t, and then with my SNS dot axis style, let's make this white, SNS dot joint plot. So x is equal to x and y is equal to y, and the kind is equal to hex, and finally the color is equal to any color that we want. So we write k, and the result will look like this. Of course, the color can be changed, so you can make it green, right? And you will get a plot like this. We can also plot the kernel density estimation procedure and visualize it as a bivariate distribution. So this is called the contour plot. Again, it looks really nice, but not used very commonly. So only use it if you're comfortable with the use cases. So SNS.joint plot, x is equal to x, y is equal to y. My data is the data frame, and the kind is equal to KDE. Once we do this, the result will look like this. It's called the contour plot. We can also draw a two-dimensional KDE plot. Let's do that as well. So this is my 2D. So f ax is equal to plt dot subplots, and my figure size is equal to 6,6. SNS dot KD plot df dot x df dot y, ax is equal to ax. Okay, what else do we need now? So we need the rug plot. So the rug plot would be df dot x. The color, let's say, is red, and the axis is axis. All right, and the final thing that we need to do is rug plot, where my df dot y vertical is equal to true and ax is equal to ax. So the result will not come. Let's see what the error is. One moment. Okay, I forgot a comma here. Right. So the result looks like this, which is a rug plot along with a two-dimensional KD plot. If we want to show the bivariate density, in a more continuous manner, we can simply increase the number of the contour levels. For example, if you want it to be continuous, we can say the same thing as earlier. So I'll copy my first line, and then we say cmap is equal to SNS dot cube helix underscore palette And as CMAP is equal to true, we will keep our dark as 0 and we'll keep our light as 1 and the reverse as true. Once you've done this, the KD plot can be presented like this. So dfx, dfy, CMAP, CMAP. The levels is, let's say, 70 and the shading is equal to true. Right? So the result will look like this. Of course, you can decrease the levels if you want to. So you can make it 25 so it appears like this. So it's a little different. If you turn the shading off, then it appears like this. The joint plot function uses a joint grid to manage the figure. Let's see an example. So we say SNS dot joint plot where x is equal to x, y is equal to y, my data is my data frame, the kind is our KDE, and the color is, let's say, R. Then we have our we have a plot underscore joint PLT scatter. C is white, S is equal to, let's say, 30. The number will come without the double quote, and the line width is equal to 1. And we'll also keep a marker here. So we'll keep the marker as, let's say, a plus sign. Then g.ax underscore joint dot collections set alpha, and the final line that we need to write is access labels and we will write $x and we will write $y. Okay, there seems to be some problem. Let's quickly check. It says the name plot joint is not defined. Okay, I'm sorry. I don't know why I wrote it like this. G.plot joint. And it is again giving us an error. Line width. Okay, so I spelled that incorrectly. Let's fix that. Line width, line width, line width. Silly mistake. Once we've done this, we should get the visual like this. Let's see how we can visualize pairwise relationships. For this, we use the pair plot, and we use this when you want to plot multiple pairwise bivariate distributions in a dataset. Right? So this would create a matrix of axes and show the relationship for each pair of columns in a data frame. Let's take an example. So iris is equal to sns.load underscore dataset, and we will select iris, and we can say sns.pair plot and iris, and what will happen is we will get very nice visualization that looks like this. If you want to, you can also specify the hue parameter. So you can say the hue is, let's say, the species, and the result will look even better. Now the result looks like this. And finally, like the joint plot and the joint grid, the pair plot is built on top of a pair grid object, which means that you have some additional flexibility. So let me do one last example for this chapter. G is SNS dot pair grid iris. Then we have G dot map underscore diagram SNS dot KDE plot, and finally G dot map underscore of DIAG. We have SNS dot KDE plot, and we will keep the number of levels at, let's say, 7. Okay, misspelled it. Let's fix this quickly. So we have the pair grid, and the result will now appear. Okay, there seems to be some problem. I'm not sure. Okay, it took a little bit of time. By the way, this does take some time, all right? So don't worry if it takes a few seconds or so. This is how the final result would happen. So that concludes our lecture, everyone. And in the next lecture, we will look at how we can visualize linear relationships.